So here are the solutions to the first problem set. So just take one and pass it around. There should be more than enough for everybody in here. The practice midterm? Yeah, that's a good question. So here's the plan. So the PS1 solutions are going around right now. PS2 is Gavin's grading it right now, and I will hand it back on Friday. The solutions for PS2 I'll also pass out then on Friday. I'll pass them out today, but there's like somebody who's actually not turning until Friday, so I can't do that just yet. The practice midterm, or some samples of practice midterms, basically like previous year's midterms, I will post this afternoon, probably around like 5 p.m. or so, and those will be on BSpace. So the solutions I don't put on BSpace just because we do use some of the same questions in subsequent years. So I mean, I know that even the paper one, somebody could like scan in or something like that, but it makes it like slightly more difficult for people to recycle solutions into previous years or into subsequent years. But the problem, the midterms, of course, I'll just post those on BSpace, so you don't have to physically pick them up or anything. So office hours today, originally I had to leave at 4, so I was going to cancel them. But now I could stay, but it kind of depends on people's preferences. So when I was going to cancel them, I was going to have no office hours today, and I was going to basically take the normal slot from 4 to 5 and put it on Monday as like sort of an extra set of office hours if you want to come in and talk about stuff related to the midterm. So I'm still willing to do that, but I don't know sort of what people's preferences are. So if you would prefer that I have just like stick to the normal office hours, so basically be today, and then the next one will be Tuesday, raise your hand. The other possibility will be that I will basically cancel today's and then just have next Monday, and then of course Tuesday as usual. So if you prefer to keep today's office hours and not have office hours on Monday, raise your hand. If you prefer to have office hours on Monday and not keep today's office hours, raise your hand. Okay, so that's an overwhelming consensus. So there will be office hours from basically after class on Monday. There will be office hours.
So for the midterm solutions, are we just going to talk about them?
No, I'll post solutions for the midterms too. I don't know if I'll do it right when I post the midterms, but I'll do it shortly. So you can look at the solutions. We'll talk about them. So then today we're going to talk about air pollution. So we'll do like course-related material stuff today. Friday I'll basically just talk about like the previous midterms, the ones that I post this afternoon. And then Monday I haven't quite decided. It might be like a 50-50 mix. Like I might finish out this lecture if we haven't finished it, and then also just talk a little bit more about the midterm.
So on Monday, we have to start with interview before class.
Yeah, so it'll be like right after class. Turn on the lights, you say? Sure. Okay, are there any other questions regarding the midterm or problem sets, things like that? Okay. So last time we were basically talking about like the relationships that people estimated between changes in air pollution and infant health, so like infant mortality. And we're mostly done with that, but there's actually like a couple other papers, like so I told you, like there's a lot of literature looking at the effects of air pollution on infant health. And there's more even than I'm summarizing, but there's like a couple others that I think are pretty neat that I'll just briefly discuss here. So there's one by Chris Knittel and Doug Miller and Nick Sanders that basically uses variation in air pollution that's generated by weather and traffic. And so at the end of the last lecture, we talked about this study where they essentially tried to measure like pollution levels by zip code and then match up like infant mortality by like address of the mother and see whether or not sort of short-run increases in pollution in a given zip code were correlated with increases in infant mortality in those zip codes. And so Knittel and Miller and Sanders basically have the same data, this sort of like address level birth outcome data and then also the pollution data. And they do a couple things. First, they replicate that original paper. So replication is something that's like useful, but unfortunately the profession doesn't really reward. So just to give you some sort of insight into like how economics as a science works, essentially, so if you have a big result, like something that people think is interesting and that hasn't been shown before, then that's very likely to get published, and it's likely to get published in a good journal, and then that will cause you to sort of get promoted and so forth, and you have enough good publications and so forth. So researchers have strong incentives to try to find these sort of big results that haven't been established in the literature. But if you sort of find another, so if you go and try to kind of like replicate the same type of study that's already been done, maybe with a different data set or in a different context or something. Ideally, like people should be doing that because it's a useful thing to do, and it's a useful thing for a couple of reasons. One reason is that any study could potentially have errors in it, either in the sort of fundamentally in the research design itself, or the researchers might have made some sort of errors when they were trying to implement the research design, like they might have written some computer code that wasn't right. You would be surprised at how often this happens. But so just because like one study found something doesn't mean that we shouldn't try to ensure that finding also holds in different contexts or in different data sets and so forth. So one thing you want to do is try to guard against errors or catch errors. The other thing is that there's something that's called publication bias, which basically comes down to the fact that it's hard to get published unless you have a significant result. So this is actually related to that whole cancer cluster thing that I talked about a couple lectures ago, and maybe it's not immediately clear how it is related, but basically in both cases, what you're worried about is that if you try, so if there's no actual statistically significant effect, like there's no relationship between two variables, but you try enough times to test for a relationship between those two variables, then eventually, sooner or later, just by chance, you're going to come up with a statistically significant result, right? Because the definition of statistical significance, if we say a result is statistically significant at the 5% level, what we're saying is that if there's no true relationship between those two variables, the chance that we would have found the correlation this large between them is 5% or less. But that means that if you do 100 different independent trials, eventually you're going to find a result that's statistically significant about 5 times, right? Because there's a 5% chance that you're going to find such a result. So in the cancer cluster case, what that means is that if you looked at 10,000 different communities, you would find sort of abnormally high levels of cancer in those communities at least a few times, just because you're looking at so many different communities. In the publication bias results, or the publication bias context, what it means is that if there's a bunch of researchers out there and they're all writing papers about a particular topic, maybe, so they all sort of are testing for, let's say, the relationship between infant mortality and pollution or something, right? So if you actually had 20 different researchers all trying to test for that, and there were no true relationship, it would still be the case that 1 out of every 20 of those researchers should find a statistically significant relationship, just because even when there's no true relationship, there's still a 5% chance that you're going to find something. And if we kind of like just were able to see the results of all 20 of those researchers and say, oh, 19 of these guys found nothing, and then this one person found something, we'd probably be like, okay, well, I don't think there's that strong relationship there. But if the publication process works as follows, which sadly is how it works, that 19 of these guys submit papers, or women, of course, submit papers to journals, and the journals are like, well, this isn't really a statistically significant result. We don't think it's that interesting, so we're not going to publish it. And then the one person who finds the statistically significant result, in fact, gets into the gets the paper published. Then when you just sort of look at the body of publications, you're going to think, oh, there's a significant relationship here. But really, what's happening is sort of the biggest result was the one that got published, and all the results they kind of found there was no relationship. All the papers that found there was no relationship didn't get published. So one way to sort of guard about that is to say, okay, well, if something gets published, then we should replicate it, right? Because in like a different data set or different context, because if it was just a fluke result, then the chance that it's going to survive the second time in a different context when you try to replicate it with a different data set is very low. In fact, it's like less than 5%. So ideally, we would be sort of doing that, but in order, we know, like as economists, that in order to get people to do things, you usually need to incentivize them. And unfortunately, the incentives are not there to encourage researchers to sort of go and replicate other people's papers, because if you just kind of find the same thing as what they found, people are just going to say, okay, well, we already knew that. This doesn't really add to the body of knowledge, and so we're not going to publish it at all, or we won't publish it in a very good journal. So that's just kind of a sad fact. That being said, in some cases you do get replications, and so these guys, as part of their study, which was kind of looking at a different thing, they had to get sort of construct a similar data set, and so then they could try to replicate the Curry and Nadell findings, and they actually found that those results were somewhat sensitive to sort of exactly how you specify the regression. So it wasn't, that study was not maybe quite as strong as it had seemed. But then they kind of try to use a somewhat different approach, and what they do is look for variation in air pollution that's generated by essentially the interaction of traffic with weather. So the idea here is that if there's like a big traffic jam on one day, that should tend to increase pollution levels, and if there's no traffic on another day, that should tend to decrease pollution levels. And their hope is that whether or not you get a large amount of traffic or a small amount of traffic is basically kind of random, or at least not related to things that would affect infant health. And so they're going to use variation in air pollution that comes from this variation in traffic, and it turns out they kind of also have to interact the variation in traffic with like what the weather is like, just because on certain days, like if the weather is good from an air pollution perspective, then it's almost impossible to get high levels of air pollution, even if you have a lot of traffic. So it actually sort of takes this interaction between weather and traffic. But after they do that, their hope is at least that the variation in air pollution that they're finding or they're identifying should be uncorrelated with other factors that could affect infant health. So they argue this will be particularly true after they control for weather and for the day of the week. So the day of the week, of course, is going to affect traffic, right? Like a Thursday has higher traffic than a Sunday, and it also might be the case that for some reason infant health is different on Thursdays than on Sundays. I don't know exactly why that would be, but I mean, I guess you could tell a couple stories. One would be that basically medical care is different on Thursdays and Sundays, which is true because you can only basically go to the ER or the hospital on Sunday, whereas on Thursdays you could go to a normal primary care physician and so forth. The other is that infants may be sort of more or less accident prone on weekdays versus weekends, depending on who's caring for them. Anyway, so they control for the day of the week, and after they do this, they essentially find that PM10 correlates, so the particulate matter pollution correlates with infant deaths, but there doesn't seem to be a relationship between carbon monoxide or ozone and infant deaths. But basically, the standard errors for those estimates are very large, so this conclusion you could basically just say they don't have enough statistical power in their research design to detect effects. They really can't say anything at all. They just kind of have noisy estimates. So then the final paper that's on our list that looks at the relationship between pollution and infant health uses the rollout of electronic tolling on the East Coast. So this is like, so out there it's called EasyPass, but it's the equivalent of Fast Track out here on the Bay Bridge. So EasyPass there rolled out earlier than, I think, Fast Track up here basically rolled out in the late 1990s. So this is the electronic transponder that means you no longer have to stop at the toll booth and pay with cash. You can just drive right through and it automatically deducts it. And the theory here is that when you have electronic tolling, this could reduce pollution near toll plazas. So before there were big backups as people stopped to pay the toll and it took a long time to collect the cash and so forth. And after EasyPass or after electronic tolling in general, you can just zoom right through, and so there isn't this big backup, and so there's a reduction in pollution there. So the one problem that they face in the study is they don't actually have a measure of pollution near the toll plazas, right? So ideally, what they would like to show you is that they roll out this EasyPass, pollution falls right near those toll plazas, and then infant mortality or infant health basically improves near the toll plazas relative to other areas of the highway where there aren't toll plazas, so there shouldn't have been any effect from the EasyPass rollout. And they can show basically sort of the beginning and the end. They can show that there's EasyPass, and then they can show that there is a change in infant health, but they can't actually show you the link in the middle because they don't have pollution data. So you kind of just have to take it on faith that pollution is in fact changing, which you may or may not believe, but it is what it is. So this is actually a diff type design. And the way you want to think about it here is that the areas that are near highway toll booth plazas are essentially the treated areas, and then other areas that are near the highway but not near a toll booth are essentially the control areas, right? So the treated areas are being affected by this EasyPass rollout, and in theory should have their pollution reduced, whereas the control areas are not being affected because there's no toll plaza there, so it doesn't matter whether that non-existent toll plaza has electronic tolling or not. And so what they find is that the incidence of low birth weight decreases by 10% in highway areas that are near those toll booths relative to highways or relative to areas near the highway that are far from the toll booth. So if you wanted to like just draw graphically what's going on, literally you just have the highway running along, and maybe there's a toll plaza here, and so they're going to sort of define two areas. One area is going to be people that live near the toll plaza, and they think that these people are going to have reductions in pollution, and then another area is going to be people or mothers that live far away from a toll plaza, but still near the highway, and this area is not going to have a reduction in pollution. So basically what they're finding is that infant mortality in this area changes or decreases by 10% relative to infant mortality in this area when the toll plaza or when the electronic tolling rolls out. And that, it turns out, is like actually a very large effect. I mean, if you think about it, first of all, any particular factor that you might be able to change that would affect low birth weight by 10% would probably be a pretty substantial impact. And furthermore, it's not. So I would think that if you saw a 10% decrease in low birth weight just from going from like very dirty area to very dirty air to totally pure air, that would probably be like pretty substantial. But this is saying that in fact going from like maybe somewhat dirty air to like somewhat non-dirty air is causing a 10% decrease in low birth weight. So definitely the effect is very large, and how you want to interpret that is kind of up to you. On the one hand, you could say, well, I guess that means that so this localized air pollution near highways must be a pretty important determinant of infant birth weight. On the other hand, you could say, well, maybe this is getting a little bit too large to be plausible, and maybe there's some sort of confounding factors that essentially are changing near these toll plazas and aren't changing near or further away from the toll plazas. Okay, so that kind of summarizes the literature on infant health and air pollution, and it turns out that there's much less credible evidence about the effects of air pollution on adult health. So the evidence, the sort of body of work on infant health is much larger and I think sort of more credibly estimated. And in part that's just because people really care about saving babies, like nobody's ever going to be against that. But there's also essentially this fundamental statistical reason, which I think I referred to earlier in the past lecture. But the idea here is that these infant health papers are all leveraging relatively short-term variations in, or relatively short-term changes in air pollution. And that's kind of a feasible thing to look at because infants haven't been alive that long and the gestational period is relatively short. They're only in the womb for 9 months and then maybe they're alive for like a year or two. So if you had like a 1-year spike in air pollution levels, then you could say, well, over that infant's entire lifetime, air pollution levels were higher than for say an infant who was born 3 years earlier. But if you're thinking about looking at adults, that same kind of short-term fluctuation in air pollution is only going to have a minimal impact on the total amount of air pollution that that adult has been exposed to over his or her entire lifetime. And because of that, it's basically infeasible to use these diffs and diffs type research designs to measure the effect of long-term exposure to pollution on adult health outcomes. And the reason that we care about sort of getting these short-term fluctuations or using these short-term fluctuations in pollution to measure effects is that we think that sort of a short temporary fluctuation that occurs very quickly is the least likely to be correlated with other confounding factors, right? So if something happens almost instantaneously, then unless there was some specific reason that it happened and that reason would generate some effect on the outcome, you wouldn't typically think that there would be something else changing behind the scenes that could affect the outcome that suddenly. Whereas if I tell you that it's always been the case that say Pittsburgh has really bad air pollution and that Seattle has really good air pollution, you might believe me that fact is true, but you also probably think that there are a lot of things that are different about Seattle than are relative to Pittsburgh, and that those things might also have some effect on people's health and longevity. So the bottom line is it's very difficult to find what we would term like quasi-random variation in long-term exposure to air pollution. So these long-term differences across regions are going to be correlated with other factors. And even if you thought about randomly assigning air pollution to different areas, it turns out you'd still have the problem, right? Because people can sort themselves in and out of areas. So let's say like we started off back in like the 1790s or something when the US had just started. And even though I don't think they really knew about randomized controlled trials back then, let's pretend they did. And they were like, okay, we want to figure out like the effect of air pollution on long-term health, even though they also didn't know about air pollution back then. And so we're going to like randomly assign certain states to have high pollution levels and randomly assign other states to have low pollution levels. And because we have random assignment, then we know that eventually we'll be able to measure the causal effect of air pollution on longevity. The problem is that as long as people are allowed to resort themselves between states, then the randomization can basically break down, right? Because even if you initially randomize, and so that the types of people who are in the high pollution states are similar to the types of people who are in the low pollution states, after a while, like probably the wealthy people are going to be like, screw it, I don't want to live in a high pollution state. I'm going to move to a low pollution state. The poor people maybe can't afford to move, and then you're back to having a selection problem or an omitted variables problem that you were trying to avoid, right? Because now the high pollution states only have poor people, and the low pollution states have both rich and poor people. So this turns out to be a really difficult problem. And what I just described is sort of a classic issue in estimating what we call effects related to environmental justice. So environmental justice is like the idea that that there's sort of these pollution havens that cluster near where lower income people live. And one question that's never clear so statistically that's true. It is true that you're more likely to find a high pollution or a polluting facility, like say Richmond. You have refineries, and Richmond also tends to be poorer than Berkeley or Orinda or something like that. So you're more likely to find like polluting facilities in poor areas, but it's really clear sort of which way the causality runs, right? So on the one hand, you could think that the poor households are there first, and then the polluters basically like intentionally move next to the poor households because they know that they have the least like political clout and are least likely to kind of block opening up polluting facilities. So it may be sort of that the poor households are there first and the polluters move in. On the other hand, it can also be the case that the polluters were there first and the poor households are moving in, right? So it's not that they're moving in because they like pollution. Of course, they dislike pollution. But it's going to be basically the case that housing values are cheaper near the polluting facilities. And so, if your income is lower, you may have very little choice but to live in an area where you have low housing values. So there's, again, this sort of sorting that's going on that would eventually potentially happen even if you like randomly assigned where polluters were located without regard to the income of the people living there. So the bottom line is that it's very difficult to generate convincing estimates of the effects of long-term exposure to air pollution on adult health. That said, there is compelling evidence of the effect of short-term fluctuations in air pollution on adult health. So there's this one study that I think is very nice by Ransom and Pope that examined the effect of steel mill operations on hospitalizations and deaths. So this is basically, you could think of it as kind of being like, so we had the leukemia cluster study that looked at the value of statistical case of leukemia. And you can kind of think of this as being like the equivalent of the leukemia cluster study, except looking at the effect of air pollution on hospitalizations. So what they do is they identify this area in Utah where there was a single steel mill that was generating the majority of the particulate pollution in that valley. So there was a valley that has a population of about 200,000, and there's a steel mill that operates there, and it turns out that 50 to 70% of particulate pollution is generated by that steel mill. So that's going to be basically what you can think of as a treated area. But then there's also a control area that's nearby. Another nearby valley has about 70,000 people living there, and it's not affected by that steel mill's operation. The two valleys are demographically similar, so they have like similar looking populations in terms of income and race and so forth. But from August 1st, 1986 to August 31st, 1987, so basically for like a 1-year period, the steel mill shuts down due to a labor dispute. So there's like a strike, they can't run the mill anymore, and suddenly this big pollution source disappears from the treated valley. And so what they do is they basically compare changes in hospitalizations in the steel mill valley to changes in hospitalizations in the nearby valley that doesn't have a steel mill. And they find that bronchitis and asthma hospitalizations fall by about 20% in the steel mill valley, but rise by 8% in the nearby valley that is not affected. So you're basically saying that, look, there's 20% drop in hospitalizations or these specific hospitalizations after the steel mill closes down. But in fact, that drop, like using that drop as the estimate might be overly conservative because in the valley that wasn't affected by the steel mill, there was actually an upward trend during the same time in hospitalizations. So if anything, sort of other factors that might be affecting hospitalizations are probably increasing. So if you do the diffs and diffs estimate there, you basically get like a 28% drop in hospitalizations with the closure of the steel mill. among preschool-age children, there's even there's an even larger effect. So hospitalizations fall by about 50% in the Steel Mill Valley, but only 8% in the Control Valley. And they actually find some change in mortality too. So there's like a 3% reduction in mortality in the Steel Mill Valley and an 8% rise